Okay, can you share? Can you see my screen?
Yes, we can. And all the cursor is there. Good. Let's maybe wait a half minute.
Okay, and you can also see my cursor.
I can see the cursor. The sound is very well.
Perfect.
And I think slides will move forward too.
Sorry?
And I think the slides, maybe you can try the slides.
Yes.
Yeah, that's good. Okay. Okay, welcome back to our second session of the second day. Our first speaker is Alireza, and please go ahead.
Thank you very much. It's an honor to be here and give this talk in this symposium, and particularly after these two great talk of Mark and Deepak. I'm going more further from AI and more towards neuroscience, and we'll talk more about novelty and surprise and their effect on exploratory and adaptive behavior in human sequential decision making. And before starting, I would like to mention that most of the stuff I'm going to discuss and present today can be found in these two papers or recent preprints on bioRxiv and or new publication in neural computation. To start with, I would like to start with this real world example. As soon as we have this real symposium, the symposium was real, you wanted to come to EPFL and give talk in EPFL. So it is the map of EPFL. You're here at metro station, and here is the conference room. Because of some miscommunication, you don't know the place on the campus, and no one is on the campus. So the first thing you need to do is to search for the conference room in the campus and explore the environment. And whenever in this talk I talk about exploration, I mean this situation that you know there exists a reward in the environment, but you don't know the environment and you want to find that particular reward. So it is not necessarily in trade-off with exploiting already existing reward. So there is one reward, you want to find it. But then the question is that how do we find this reward? How do we explore the environment? How do we search? Do we do just a random walk and random search going to random direction, or do we try to define some intrinsic measure of progress and follow that? For example, going toward the places that is more surprising or more novel, as we saw a few examples before today. But no matter which one you take, at some point you would end up in the conference room and you are rewarded. And in the following day, you are in the second phase, which I call exploitation. Every day you come to the EPFL metro station and you take one of the routes that you know goes to the conference room, and you follow this, and so far so good. The conference is over, you're back at home. 1 year later, you're again back in EPFL, and there is the second symposium. But because again, some misinformation, the location of the conference room is changed, but you're not informed. So you take the path that you already think goes to the conference room, but that you're surprised and you see that you were wrong. So the third phase starts here that I call adaptation. And in this adaptation phase, your job is to research the campus, explore the environment, and find the conference room again and adapt your behavior to the new situation. And today I want to ask this question that how do humans solve such complex tasks through these three phases? And there are already many established results in the field about these three phases. For example, the first phase of exploration, very similar situation, very discussed in the field. And they were usually linked to curiosity and intrinsic motivation. And people hypothesize that humans seek surprise or novelty in a combination of them. The second phase is studied under the title of reward-driven behavior, and the third phase is usually linked to surprise and surprise modulation. But there are still many debates and open questions. In this talk, I'm going to focus on the first phase of exploration and the third phase of adaptation. As we saw, if these two are related to surprise and novelty, then the first question that arises is that how can surprise and novelty be distinguished formally? There are many ways to talk about this, and you can look at this amazing review paper of Andrew Bartow that discuss many of different formal ways to discuss them. But it is clear that there's not a unified way to do that, and there is not a clear agreement on that. The other question is that in this situation that we know the reward is distributed sparsely, so there is one reward and we want to search for that in this kind of exploration, what drives exploration, surprise or novelty or not? How do we search this environment? And on the side of adaptation, we know that surprise is relevant to adaptive behavior. But then the question is that how does surprise contribute to adaptive behavior? And more importantly, how habitual and planning behavior interact with each other to adopt the behavior. So what I'm going to do today is first start on the theory side, give definitions for surprise and novelty, then go and formalize their contribution to exploratory and adaptive behavior by developing an augmented RL algorithm. Then on the experimental side, we would design a deep sequential decision-making paradigms very similar to the example, and test our augmented algorithm on the levels of behavior and EEG. So first I would talk about the theory results, then experimental result, and at the end I would talk about the conclusion. So as the starting point, we start with the simple MDP setting in an RL framework. We have a finite set of states, for example, the different places on the campus, a finite set of possible actions, different directions that you can take. You start at the metro station, this S1 in this set. You take one direction, one action, go in that direction. You end up in a new situation, in a new place, and you receive a reward. And this reward can be, for example, whether you are in the conference room or not. And you take another action, so on and so forth, until time t. The dynamic of this process has two components. One is the way that actions are selected, which is under control of agents or humans, and we call it policy. And the other components is how, given these actions at these states, the next reward and next states are observed and achieved, which can be summarized in this expected reward of this transition, as well as the transition probability, the probability of this transition. So the assumption here is that these two functions are not known and are going to be estimated by the agent or humans as the word model. And then this word model can be used to make a policy by model-based planning approach or model-free habitual behavior, which in the model-based approach, you estimate the map of the environment and try to plan and make your next action. And the habitual behavior, you reinforce the sequence of actions that already gave you some reward. So given this framework and given this setting, how do we define surprise and novelty? Before going to formal definition, I would like to look at natural language and take Oxford Dictionary and look at the definition of novelty. Novelty defined is the quality of being new, original, or unusual, and to a new or unfamiliar thing. In this work, we are going to focus on unusual and unfamiliar. So we do not necessarily think about as a novel thing as something which is not in the memory, and it is original or new, something which is less encountered. We call that something novel. But on the other hand, surprise is defined as a feeling of mild astonishment or shock caused by something unexpected, an unexpected or astonishing event fact. So while novelty is about being unusual and unfamiliar, surprise is about being unexpected. And at the same time, when novelty is defined about a thing or assigned to thing, surprise is assigned to events and facts. So in the framework that I discussed, in this RL framework, the way that we are going to translate these two notions is to define novelty as something to measure how infrequent or frequent a state is, while we define surprise as something to measure how unexpected or expected a transition is. And to quantify this measure of being frequent and being expected, we define this probability, N here stands for novelty, and a probability of observing state st plus 1 at time t. We consider this to be the proportion of time that you have spent at state st plus 1. Ct of st plus 1 is the count, is the amount of time that you spend at the state st plus 1 until time t, and t is the whole time so far. So this is the ratio of which proportion of time you spend in this state. And just I wanted to mention, I'm very happy that Mark today talked about that. These notions are used in reinforcement learning and machine learning as density models. And they are somehow in contrast with what people call word model, which are about that what is the probability of a transition. So this was about how frequent or infrequent a state is, while such a probability is about what is the probability of going from this pair of state and action to the next state, and how much this transition is expected and probable. And this is what subjects and agents estimate as the word model. And this has a very similar shape to the other one, to the probability related to being frequent. But the difference is that here we have the count of how many times you experience this transition divided by how many times you take action AT at the state ST. So the main difference between being how frequent and being and how expected the transition is about this conditioning on the pair of state and action. And using these two measures, we define novelty of a state as minus logarithm of this probability, which this minus logarithm comes from the literature. And for the surprise measure, we define surprise as 1 over this probability of how expected something is, which we call base factor surprise, and we recently showed that is very relevant and crucial in learning in volatile environments. So to summarize, novelty measures how infrequent state is, while surprise measures how unexpected a transition is. And what I'm going to do next is to formalize their contribution to behavior. We make an oral model with 2 principles. The first principle is that adaptive behavior is a result of surprise modulated learning. Or as our motto, I'm surprised, therefore I learn. And our second principle is exploration is driven by novelty. And as our motto, it is novel, therefore I seek. How to formalize this? We formalize these 2 principles via surprise novelty reward algorithm, and we call it SURNOR. Similar to what it was discussed since yesterday, this model receive a sequence of states and reward, and is trying to find a policy which maps the states to distribution over actions. The starting point of us was this classic standard hybrid policy designed by Dow and Glacier years ago, which has one planning branch and one model-free TD learner branch. The planning branch estimates the transition probabilities and reward function and assign values to actions at each state. And the TD learner reinforces the sequence of actions that lead subjects and agents to a reward via reward prediction error and TD errors. And again, assign some values and to pair of state and action, and then combine the 2 policy and choose the next actions. What we do next is add this novelty block to this model, which use novelty as an intrinsic motivation. And I want to emphasize that we treat novelty exactly parallel to reward. So we define, similar to what we had value, reward-based value, we define novelty-based value. And as soon as you define novelty-based value, in the model-free TD learner, we introduce the TD learning of the novelty values as novelty prediction error. And the third step that we have is adding surprise as a modulator of learning. As I discussed before, being expected depends on the model of the word. The word model is in the model-based branch. Surprise is calculated by how expected a transition is, and this surprise value modulates the learning of the word model, as well as model-free action values. To summarize, our contribution on the modeling side is the particular definition of novelty as using it as an intrinsic motivation, separation of reward-based and novelty-based value. So we are not basically summing novelty and reward together and having a single reward value. The second point leads to the third point, which is introducing novelty prediction error as a new learning signal. Later on, I will show that this turns out to be a very important signal in both behavior and EEG. And at the end, our first contribution is this new interaction between model-based and model-free modules via surprise modulation. So far, I define novelty and surprise, formalize our hypothesis in a computational model, and now we are going to experimental results. So we design a deep sequential decision-making paradigm, which I will discuss that why we call it deep soon. And we asked 12 participants to do the experiment. At each time, they saw one image on the computer screen. This image here, a cup of tea or coffee, corresponds to state as T. They had some time. They received 4 gray disks below the image. These are representing the actions, and one action is chosen here, and we call it a T. And after a while, you observe the next state, which is a picture of the lamp. And you continue this until the point that you find the goal state, which is a thumb here. And we call this whole process one episode. Thinking about this environment and this computer screen, and thinking about the example that I had before, this is similar to thinking about the first vision of you when you're on the EPFL campus. So you see something like this while you are, if you look at the top and in the map of EPFL, you're on this environment while your visual input is some building and some people around. So similar to this map, there's also some underlying map for this environment, for the experiment, where has 11 states. One of them is the goal state, where you want to find, for example, is corresponding to the conference room. And state 1 to 7, for example, state 1 corresponds to the cup of coffee, state 2 corresponds to the lamp. State 1 to 7, we call them progressing states, because at each of these states, you can take one action and go one step closer to the goal state. And these states 8 to 10, we call them trap states, because 2 actions from each of the progressing state put you in the trap states. And when you are in them, 3 actions keep you there, and only 1 actions let you go out. And when you go out, you go actually at the beginning of this track to the goal state. So when you're on this progressive state, you can go forward and find the goal state. But as soon as you do one mistake, you go to the trap states and you stuck here for a while, and you need to find this good action to start again from the beginning. Participants do 10 episodes in this environment. The very first episode is similar to phase 1 of exploration. So they know there is a goal, and they're in this environment. They found to find the goal state. The environment is quite difficult. If you do random exploration, if you choose each of the actions with 1/4 probability, the expected number of actions until then you will find the goal state is 10,000 actions, while human participants solve the task in around 100 actions. It kind of shows that humans are not definitely using random exploration. After finding the goal state, we are in this phase 2 of exploitation. So every time they start anywhere, they go quickly to the goal state and don't spend any time in any other places. But then to have this adaptation phase, this change of the place of the conference room after a year, before episode 6, which we call them second block, but a participant doesn't know this. We swap state 3 and 7. So state 7 was before here. And when participants were here, they knew that, okay, if they take this action, they go to goal state. But when we swap these 2 states, they kind of lose their only path knowing to, the only path they know that goes to the goal state. And they need to find the goal state again and adopt their behavior. What we observe, which is interesting, is that they're much faster than the first time finding the goal state. It means that they could search the environment, but at the same time, they were using the accurate knowledge before. So they were using what they learned before, the structure of the environment, what are the good states, what are the bad states. And but they could at the same time adopt their behavior. And then we had another 4 episodes for the exploitation. So to summarize, participants use a smart exploration strategy, which we hypothesize that is novelty seeking. They adopt their behavior while using the knowledge acquired before, and we hypothesize that this is done via surprise modulation. So what we are going to do next is testing these two hypotheses that I mentioned before, which were formalized in Sooner algorithm. So what are our alternative hypotheses for Sooner and these surprise modulation and novelty seeking? We have three levels of alternative hypotheses. The first level is in exploration strategy, learning styles, and policy style. For exploration strategy, this is novelty seeking, which is used in Sooner. As an alternative, we remove novelty module here, and we use optimistic initialization, which basically means that assuming there is no need for a notion of curiosity or intrinsic reward, external reward by itself can drive exploration. And then still removing the module of novelty, we use what Deepak just discussed in his talk, following mismatch and following uncertainty or surprise. So we used logarithm of a surprise, which is surprisal, and it's exactly similar to what is used before in machine learning community as the intrinsic motivation. And this is another alternative that we have here. For the learning style, we had the surprise modulation, which is the case in Sooner. And in addition, we removed the surprise modulation and had a constant rate of learning and forgetting for both model-based and model-free. And finally, for the policy type, we have the hybrid policy. So both planning and habitual behavior affect the policy. We have the model-free policy, which we remove the planning part of the policy, but still the model is equipped with a word model. So still surprise can affect model free. So there is a word model, but the agent or subject does not use it for planning, but use it for computation of surprise. And at the end, we have model-based policy, which we totally remove the model-free block. So for example, and we kind of combine all of them together and have all the combination. For example, when I write MF plus S plus U means that model-free policy with surprise modulation and with uncertainty seeking. And Sooner is equivalent to hybrid policy plus surprise modulation and novelty seeking. So what we observe fitting the models to human behavior and looking at the expected model posterior, so which model is more likely to generate human data, we can find that Sooner algorithm, and by the way, this is protected exceedance probability. Sooner is by large margin, the most probable model. And the next one is model-free plus surprise and novelty. This shows that all modules of hybrid policy, surprise modulation, and novelty seeking are needed to explain the human behavior. And these here show that even the next most likely model, only the model-based module is removed. So still we have surprise modulation and novelty seeking. And in addition to outperforming the other models, Sooner could predict human participants' action in a trial-by-trial basis with a very, very high accuracy rate. It could explain, it could predict 51% in the exploration phase. And please note that at the beginning of the exploration phase, we don't know anything about the participants' idea about action selection. In the exploitation phase, we predict around 90% of the action, and in the adaptation phase, around 56% of the action. So to summarize, both model-based and model-free contributes to action selection. Novelty seeking explains participants' exploratory behavior better than its alternatives. Model-based surprise modulates the learning of the word model as well as model-free action values. So what we are going to do next is a closer look at the model-free model-based interactions and look at their effect size. So model-based and model-free in our algorithm had two types of interaction. One was through passing the surprise of model-based to model-free learner, TD learner, and modulating its learning rate. And the other was combining the policy of model-based and model-free through hybrid policy. Looking at this link, model-free surprise at time t is a function of model-based surprise at time t. In this graph, we see surprise on the x-axis and model-free learning rate on the y-axis. And the curve is found by fitting the model to human behavior. And if we look at the distribution of surprise values, the histogram of surprise value, what we can observe is that for surprising transitions, which are here, the learning rate can increase up to 8 times comparing to the learning rate of non-surprising transitions. So this surprise modulation really has a significant effect on the change on the learning of model-free learner. But if we look at the hybrid policy, that how model-free and model-based affect the policy, we can see this curve. On the x-axis, we see different period in the experiment. E1 means phase 1 exploration. Here is adaptation, and these two are exploitation phases. The y-axis shows the dominance of model-free in the action selection policy. And what we observe, and 1 here means model-free and model-based have equal contribution. What we observe is that always model-free dominance action selection, and moreover in the exploitation phases, the algorithm is almost model-free, and this is what also we saw in the model fitting, that the second best model was model-free plus surprise modulation and novelty seeking. So to summarize the behavioral results, novelty seeking explains participants' exploratory behavior better than its alternatives. Participants use their word model only rarely for action planning and mainly to extract moments of surprise. And model-based surprise does not only modulate the learning of the word model, but also learning of model-free action values. Now what we are going to do is to look at the model variables and how they're reflected in EEG signal. The experiment that I discussed before was that you observe this image. After observing the state for 650 milliseconds, we recorded the EEG signal and averaged over these electrodes. And at the same time, and after the experiment, we fitted this model to the behavior and found the model variables surprise, novelty, RP, and NP. So for each time point, for each ST, we have one surprise value, one novelty value, one RP value, and one NP value. And we have 650 milliseconds of EEG. We compute the correlation of each of these variables with the amplitude of EEG in these 650 milliseconds. And what we observe is that we have a positive correlation window for surprise around 300 milliseconds. And when we look at novelty, we have a much broader positive correlation around 300 milliseconds, as well as a negative one later on. So this is interesting for me because earlier today, Mark was saying that these density models, he cannot link it to biology. While we can see that this model of the world and these density models, how frequent something is and how expected something is, are reflected differently in the EEG signal. And we can look at also at RP and NPE, and we can see similar thing here that RP is more similar to surprise, NP is more similar to novelty. One can ask that whether these all positive correlation around 300 milliseconds is because of cross-correlation of different model variables. Because of that, we control it by multivariate regression and some orthogonalization. I'm not going to show the whole results, but the main result was that around 300 milliseconds, we saw positive and separate and significant contribution of all of different signals, and more importantly, the NPE, this novelty prediction error. So now I'm going to make the conclusion. Our original question at the very beginning in the introduction, I said that we focus on exploration and adaptation phases. The first question was that how can surprise and novelty be distinguished formally? When reward is distributed sparsely, how do humans explore? What drives exploration, surprise or novelty? And the third question was, how does surprise contribute to adaptive behavior, and particularly how habitual and planning behavior interact to adopt the behavior? Our answers and take-home messages. Our first motto is novelty is not surprise, and we showed it on formal definitions, contribution to behavior, and signatures in EEG. And this is mainly because this fact that being frequent is not equivalent to being unexpected. Our second motto is it is novel, therefore I seek, and in particular, which give rise to this NP signal that we saw that is as important than RPE. Yesterday, Andrew Barr said that he was interested in novelty because it is coded in dopamine neurons. Maybe this NP signal can give us some clue that what is the function of these novelty dopamine neurons in the VTA. And as our third motto, I'm surprised, therefore I learn, and more importantly, modulation by model-based surprise is necessary for both model-based and model-free learning to explain adaptive behavior. I would like to thank my amazing collaborators and our lab here. And again, our papers or results can be found in this paper, in two papers. Thank you very much.
Thank you, Alireza. Are there questions? And again, I'd like to remind the speakers that they can unmute themselves whenever they want or raise their hand, because I saw that Jacqueline had a question, but she put it in the chat. Okay, I don't.
I have a question as well. Do you hear me?
Yes, go ahead.
Yep. Yeah, thanks very much for the great talk, Alireza. I kind of have the obvious question. I don't know whether you remember our exploitative agent yesterday, which was after Bayesian surprise. So do I somehow understand it correctly that your measure of novelty is closely related to Bayesian surprise, because it looks somewhat at this change between what is currently going on and the next step, because it has this transition aspect to it. So, or have you thought more about relating this measure to Bayesian surprise?
I think Bayesian surprise is a bit different conceptually from both this surprise and novelty measure. But if I want to say that to which one it is more related to the surprise measure that I discussed. Because Bayesian surprise is again about how much you change your belief about the word model. So you're again thinking about the transition, that how much I change my belief about the transition probabilities. And based on this, this fact, I would say that it is more related to the measure of surprise that we define here.
Okay, so because you basically you basically have a belief about the transition probability and not the probability of a state itself. So that's the point then, right?
Yes, exactly. The Bayesian surprise is defined as difference between PT and PT plus one while you have conditions here. So it is not about this one, at least the way that it is defined so far is more about the word model, and it's about the transition probabilities, not about these density models.
Okay. Thanks.
You're welcome.
Good. Maybe we have a question from the audience. I will read this. Jennifer Bassel asked, wondering how you might think about novelty driving the creation of the world model at all, not just improving it. That is, how does curiosity or novelty seeking lead to the desire to understand and have a model of the world? Does that arise naturally because of the novelty prediction error? Oh, that's, I think, 3 questions, but.
Okay. Can you repeat them, because I cannot see?
Yeah, I think I will repeat it. So the first question is, I think he or she is she's wondering about how novelty drives the creation of the world model and not just improves it. And I think the second question is, how does curiosity or novelty seeking lead to desire to understand and have a model of the world? The last one is, does all these things naturally arise because of the novelty prediction error?
Okay, the first question, I should clarify that novelty here does not have anything to do with the model building. So novelty drives the exploration, and when you explore in the environments, you will learn the word model. So even if there is no reward and you can only use novelty and go around and only passively learn the word model in the background. So this is about the first question. So novelty does not improve model learning. It's about exploratory parts. And about the second question, how does curiosity or novelty seeking lead to the desire to understand and have a model of the world? I would say that the novelty seeking that we have here does not have a direct relation to a desire to make a model of the world. But surprise seeking and the way, for example, Deepak defined these mismatches and defining curiosity as as a desire to follow these prediction errors, then I would say that curiosity in that sense can be related to a desire of making a word model, because you want to decrease the surprise and you want to follow surprise and go to the places that you have less information. And the last one, does that arise naturally because of the novelty prediction error? I cannot really understand the relation of the third question to the previous.
I think the question is if you get all these things free just because you have the novelty prediction error.
I think the novelty prediction error is irrelevant to them, because still you can have the similar behavior if you remove the model-free branch at all. And only by model-based branch and planning, you can have the similar behavior without a novelty prediction error.
Okay.
I think Andrew has a question. Please go ahead.
Very interesting talk. Too much for me to absorb at the first listening. But I wonder, you mentioned our earlier paper on surprise or novelty. We found that there seemed to be a lot of confusion between the two. And I wondered if you observed that also in looking at literature that talks about surprise and novelty.
Yeah, I think that a very important thing there is to whether think about novelty as something which is a novel thing, as something which is not in the memory, or something that you encountered less often than the other things. And I think that in the review paper that you have, you very interestingly discuss all these aspects. And there, I think that it is more emphasized on the fact that novelty should be related to observing something original and something which is not in the memory and is more about memory formation. But here, the way I was thinking about is more not thinking about novelty as something that has not been encountered ever. It has been encountered, but less often than the other things. So I have been to EPFL many times, but some places are more novel for me than the other places.
Right. So it's a statistical outlier would be novelty in your framework, right?
Statistical outlier, depending on the conditions, can be both surprising and novel.
Right. So yeah, we actually it was very hard to distinguish completely surprise and novelty for a lot of cases, and so you found that as well. There's an overlap. So in the term surprisal, which is low probability, basically, would really be more closely associated with novelty, the way you think about it, than surprise. So the term surprisal is misleading.
Exactly. And then depends on when you compute the log of probability, what you put there as the probability. Is it the conditional probability or is it the marginal probability?
Yeah.
So you can put there the density model of Mark, and then you see something that I would call the novelty. And then you can put there at the same time the probability estimated by the word model, and then I would call it surprise.
Great. Very nice. Thank you.
Okay.
Okay. Here's another question from the audience by He Xiao Zhu. The question is this result task specific and potentially also paradigm specific? And the question is, if the model is unobservable or partially observable. And third question is, if you have a paradigm where you teach participants the model in one or the other way, can then the participant use model-based and more than the model-free learning?
Those are very important and good question. The first question, is this result task specific? I won't say it is task specific, but I would say that it is a class of task specific. So for this particular setting that you are going to find one reward that you know that exists in that environment, I would say that novelty seeking is more relevant than surprise seeking, because you want to see more places in the environment rather than finding a perfect model of the world. But definitely it is task relevant in some sense. And as we discussed yesterday in the discussion panel, I think that depending on what is the goal, the intrinsic motivation can change. And I think that Tom Griffiths would talk about it later today, that depending on the situation, how curiosity is defined. And for the second one, because the model is unobservable, partially observable, and this is the rest is actually, there's this new paper last year by Todd Harry that they show that if you train the subjects and you give them some very specific and clear instructions, they're more better model-based than model-free. But I think that those findings is in more simple situations and simple tasks. In these tasks, I cannot believe that we can give a structure to the participants that they are more model-based, unless we really give them the model of the world, if we really give them the layout. Otherwise, these 11 states with 4 actions at each state, I would say that it's quite difficult for someone to be more model-based there. It really needs lots of computation. I think that Jacqueline has a question.
Jacqueline, you have a question?
Yeah, I just wanted to make a point that this is a confusion, novelty and surprise. I think we'll be debating this for a while because, so for example, just to point out that if you say that curiosity is novelty-based, people in my line of work use these tests of non-instrumental information demand. Which is basically has nothing to do as a sort of operationalized definition of curiosity, and that is nothing to do with novelty, right? It's all something that you would call surprise, right? We put people or animals in conditions in which event A could happen or event B could happen, and we define curiosity as the desire to predict which one will happen, regardless of a reward gain. So that's not novelty based, but we call that surprise because it's not reward driven. So I kind of see the distinction, but I think there are many facets. And one thing that I wonder about is couldn't you define novelty as based on some other model, some bigger model of the world, so surprise you define relative to the model of your task. But you could say, well, people have other models, bigger models of what can happen in the world in general. And then novelty, you could define novelty as also a model-based surprise just related to a different model.
Those are very good points in the response to the first one. I didn't claim that curiosity is equivalent to novelty seeking. My claim was that in this particular task, exploration is driven by novelty seeking. But I agree that curiosity has different aspects, and depending on the situation, it can have different drive. So this was the first part.
I thought I heard you say that. Okay, never mind. Yeah. Mm-hmm.
And for the second one, I somehow agree with that, but at the same time, I do not agree with that. Because a model of the world, if you have a change point in the environment, you would change your expectations. But the thing is that something which is more often and more frequent would not change by a change point by the environment. So as soon as you detect a change point, you would change your expectations. But if you have observed something many times, it is still, it has been still more frequent for you, and it has been less novel. For example, when I came here from Iran, then I would not expect to eat Iranian food in EPFL cafeteria, but still Iranian food was not novel for me. So the new world model, I did not expect to eat Iranian food, but still it is not novel.
Okay. Thank you, Alireza. I think we need to move on to Jacqueline's talk.